We got to know each other when we were students here, and a couple of us are still around, like Professor Herring and myself, and where's our other geophysicists?
Round?
No, not Rob, Mike. Mike was around in that group at the time, so some of us are still hanging around here. But it was a time of, a lot of hard work in our young days. And the thing I remember the most about Arthur and myself talking about is not all this science. We used to school at a British-style school in Hong Kong, and I went to school at a British-style school in South America. And it was so incredible, the commonality and the quality of it. And, we are both thankful for that kind of education. But Arthur went on to an illustrious career in geophysics. He has mostly been interested in things in or associated with boreholes. He has been, I believe, a vice president for one of the borehole companies, or maybe more than one. And now he is a professor at the National University of Singapore. Author of a number of books, and really important to think about. ERL, that I would say we all love, maybe some people love that more than others, but we all love ERL, was founded by Professor Toxos and Professor Arthur Cheng. And so it's still here. It's still doing well. It's doing good research. It's educating students and so forth. So I don't know if you all had that vision back then, but it is still some place that is sticking. And Arthur, because he has become this illustrious person, has also contributed dollars to ERL at various times, and in fact very recently again. So we all thank him for this, that he remembers the place. And I wanted to just turn it over to Professor Toxos for a moment, because, to say something about Arthur. It's a very special bond.
Well, more than 40 years ago, when we first met, when Arthur came to graduate school from Cornell University, and I was a young faculty member on those days, and he was a very young and bright graduate student. And among other things, in addition to science, he was also one of the leaders in the department in athletics. And played soccer. He was crazy about hockey. And then when he served on graduate admission committees that helping out, is that you notice that he always favored some of the athletes, especially trying to find some good hockey players. But Arthur did a great thesis, and part of ERL's fundamental scientific areas from which it started, partly based on his thesis work. But he also went jointly with me and a couple others, and convincing many companies and to support a major research effort at a university like MIT, which was so far from Houston or Texas or any oil patches in the country. And his efforts really paid off, and that's why we have an ERL. And then other things is that, as Dale mentioned, he has been a very good friend of MIT, of the department, and of ERL. And we are very happy that as a special fellow ERL, and he is spending some time, and in the coming years and semesters, he'll be spending more time here at MIT and at ERL. I won't take any more of his time. you will be here next week, and there will be coffee hours and so on. We can talk more about what he did, or he can tell you, and I'll keep him honest about what he did.
Let's see. Is it, yeah, it's on. Yeah. So, thank you, Nate, for kind words, Nafi and Dale. We went back a long time, too long to mention, I guess. And I just want to say a couple of things before we get into the technical part. One, we talk about the VSP here, and there's the third part to formation of ERL, which is Dr. Roger Turpinning, who was instrumental in getting the VSP part going. Although now I move into quite a bit of VSP stuff throughout the years. But as Dale mentioned, we went to British schools and we lived I grew up in a British colony. Again, Dale was formerly British colony when he was actually. And this actually, those of you who are in the US who don't actually realize how much influence the British system is in this world. And I found that out in NUS. Singapore is a British colony, was a British colony, and came out left British colonialism back in 1950 something, and independent in 1960 something. I would say NUS probably, in terms of bureaucracy, more British than even the British universities. And then, funny thing is, you think this might not be politically correct to say, so it goes out to the YouTube, so might be not. I cannot say it too much, but it is. The British influence is all over the world, and I just came back from a cruise around South America, from Argentina to Chile, and all there you saw the old colonial British influence in the architectures and ways doing things. So it's interesting, just something food for thought about what's going on. So today I'm going to talk about, the other thing I should say is I'm very happy to be formally associated back with ERL as a ERL fellow, although I have no idea what I'm supposed to be doing. So, but anyway, we'll play by the years and find what's going on. So today I'm going to talk about one of the subjects that we've been doing research is at NUS, particular with Elita, who a lot of you know, not everyone, some of them are younger. She used to sit over there, and she was SCP graduate under Biondo and spent 2 years here that I recruited to go to NUS. Probably the best academic decisions I've ever made. She's that good. And then there are a couple of postdocs, Yu Du and Zhang Yang, who work with us on this project. She's one generation removed from ERL. She was Rob Stewart's student at U of H. Rob's one Nafi student doing on VSP. And Zhang is from Tongji University. So they're postdocs. Yu is back in China now, working in Aramco. So she's gone to make money instead of doing academic research. So quickly, what I'm going to do is go through very quickly, since this is a academic community. A number of you might not know what a VSP is, what it looks like, what we can use it for. So quickly go through some background, and then we quick review of what we're doing now and what they're doing in terms of imaging. So incidentally, at Overburden, my last stop before at NUS on the VSP group, we also have two of NAFI students in that, Mark Willis and Xiaoming Zhao, Xiaoming Tang's wife. So we kind of, EIL's influence is actually quite significant in the industry. So we're looking at the first time migration, the least square LTM, source free converse. This is what we're trying to talk, and then we'll talk about some of the challenges we still faces, which is model building, wave field separation, and the imaging challenges. Finally, just a very few words about, everybody talks about distributed acoustic sensing, DAS, and what are some of the challenges we see in DAS. So aim of the VSP is for well tie, the number one used for VSP, tying seismic to the well data. So on the 3D VSP, you're looking at azimuthal velocity variation around the well. Okay, and one of the things that we do in VSP, you're looking at higher resolution for the near borehole imaging. So VSP, because our receivers are downhole as opposed to surface seismic, you have one less leg of the travel time. So you get less attenuation and thus higher frequency content and higher resolution. So one of the things that a lot of people in the industry make a mistake in trying to say VSP imaging is there to replace seismic imaging. It's never been intended to do that. It's only complemented in specific situations. So a VSP is, what is VSP? It's the source on top and receivers at the bottom. The receivers are multi-level tools, okay? So historically, these tools are geophones, single-level geophones that clamped to the well. When we first started, they're single phones, and then by the time I left to go to Western Atlantic, huge, they've gone to about 5 level to 8 level. Now, the commercially used ones typically will cover 16 to 32 levels, maybe more. And then there are people who actually over 100 levels, so they're really a large coverage. Now, in the old days when we have single level tools, what we do is repeatedly shoot, and then we move the tool up. So very inefficient doing things, okay? And that's why the data is not, quality is not the greatest in that. But now with a large array, so you can much more efficiently acquire the data. So this is seismic. And take a look at the red circle there. This is just on the seismic. It's not very clear what the structure looks like. With a VSP, walkaway VSP, you get a better resolution in this area. So this is what primarily a lot of things cycle back and forth. It sharpens the dips over here and get a much better idea what this structure looks like. So this is what it's supposed to be very good at. Okay. So current approaches, what do we do now? We getting field data, we do wave field separation, getting velocity model building, we do a VSP CDB transform for most of the cases, and most people still do Kirchhoff migration. We don't do routinely RTM with first time migration because it's a bit too costly. So the VSP wave field depth and time, you can easily identify on the VSP section. The P wave arrival first, this is the red line. The blue is the P wave reflection coming back up. The green line is converted, transmitted S wave, which is the P wave converted and interfaces at continue propagating as shear waves, which is the green stuff. And the fourth one is converted refracted shear wave, which is the P wave incident on the interface convert it in S wave, and come back up as a S wave. So these are the typical wave field. So these are events you can identify on the VSP data. Now, I would just say that this is a near offset VSP data, which means that the source is close to the well. Then you can see this. When you go far offset, the wave field gets a lot more complicated. So what you then do, then you separate basically the blue and the red reflections, okay? The P wave reflections and the S wave, P converted S wave reflections, and have a section like that. So you have a P wave reflection and a P to S reflection section. You can separate them. And you can do imaging, separate the upgoing event on VSP, and you can do separate imaging and processing to it. So another thing that we usually need to do in 3D VSPs, or 3-component 3D VSPs, is doing wave field rotation, because when you go the two down there, you have no idea where the horizontals are. So basically you rotate it and maximize your horizontal, the radial components of the horizontal, we do that. Velocity model building is the near borehole velocity based on first break time picking. So you can have an interval velocity based on interval adjacent receiver picks, intermediate velocity based on the total travel time, or formation velocity based on formation top, usually identified by well log. This is probably the best way to construct your velocity, although it takes a while, become more difficult because you need to tie in the well logs. The reason being that is the receiver's spacing typically are 50 feet. So the formations can be less or more. And if you just do interval velocity, you get a lot very jumpy. And if you identify the formation tops, then you get a more smooth, a more accurate estimate of the velocity. But one of the biggest problems, of course, you're measuring the velocity near the borehole. There's no really easy way to extend it from the well. So, I'm getting a little quick because there's quite a bit to talk about. The VSP, one of the standard way to doing velocity, calculating the VSP image is the VSP CDB transform. So we have a section of wave field here. This is measured in time. How are you going to project it in terms of a trace in space? So what you need to do is you get your velocity from near offset and build your velocity model. Sometimes from the geology you tilt it a bit or not. But basically you have a velocity model. And you do ray trace from the source into the geoform location. And then because of doing the ray tracing, then you can identify each pair of reflection position in space corresponding to the arrival time. And then you take this trace and basically use this relationship and map it along this trajectory. And you get something like this. And of course, this is a nonlinear transform, okay? And so you always have a stretch over on the far side, on the deeper part of the well. So once you have a number of receivers, in this particular case we have one source, a number of receivers, but you can have a number of sources too. Then you stack it together and will look something like that. And what you do is you actually go in and resample it so that you look like a reflection. So this is a very standard way and still, in general, very much used, especially, and it's quite robust in things that you don't have a lot of geology. Okay. And you can always compare your model with the wave field. For example, here we know we're missing something, reflection. This boundary might not be correct. We have actually reflection up here. So you can actually go in and modify your model and iterate if you want to. Okay. A third part is for the seismic guys to do a lot of migration. Unfortunately, the VSP migration, because of the geometry, okay, you can see doing the standard Kirchhoff migration is trying to sum along here. We don't have enough aperture, and so we usually need a very good velocity model, and more importantly, you can see the migration smile going around, and then that's a lot of times you really need to constrain the dip angle and how much you sum it. So it becomes very artificial and too much interpreter input, and in some ways creating your answer rather than actually let the data tell you what the answer is. Okay. So for example, this is one of the first earliest 3D VSP we did on land. This is Finton Dome. This is 20 years ago now, and this volume is the VSP volume kind of slides into a seismic. Looks very nice, continuous, but this is true. I don't know how much truth that is, because the velocity background we put into this model has a lot of geological input, the dipping things in there. So at least the only thing you can say is the result seems to be consistent with the model you put in. But that in itself is not necessarily guarantee the right answer. I'll show you something later. Okay, so this is what people do up to now. So now, then I'm going to talk about imaging. So this is, as you can imagine, those who actually know me and Elita, this is pretty much mostly Elita's work rather than my work. And so the insight in seismics and surface seismic in particular, people do a lot of reverse time migration now. Basically, it's easy. You close your eyes and try to just propagate it through the grid, but then the RTM needs a very good velocity model in order to give you a good answer. So the other thing we do is least square RTM, which is turning the RTM, which is a migration problem, into an inverse problem. Okay, and then this is extended least square RTM is basically an extended version who's saying I don't quite know my velocity. I have more error in the velocity. How can I get a new extension? I get a better answer. So we're going to show you some example of the field data set. So this one, I think I have to do it. The idea to this one is I will show you this is what they call the seam model. This is a saw flank. This is my well here, I think. This is a source. So we want to give you this is different layers. We want to give you some idea what the wave field looks like in here. Okay, they come down, and you can see things that reflect back down here, are both reflecting into upgoing and downgoing. So the layer arrivals of that you hope to be able to see on the reflection of the sort flank are very complex, and at the well site, being able to pick out the reflection is not easy. So a quick lesson in reverse time migration. So conventional PP imaging condition consists of a source coming down and a receiver. You back propagate from the receiver back down. So forward propagated source wave field convolve with the back propagated receiver wave field, okay? And then that's the P, the purple is the P, the red is the PS, P converted S. So we have an imaging condition. This is the thing we published in October, SEG Geophysics last year, October issue. So this is the very straightforward. So this square RTM, high resolution, balanced amplitude, receive artifacts. So RTM is just basically this operator, which is the jump on the data, the migration operator. Okay. Least square RTM is basically constructed as a least square problem. So you guys at MIT, you know. We used to joke that nobody graduates here without putting this equation in the thesis, right? I have that equation in my thesis. I'm sure Dale has that too. So we're very familiar with the least squares problem and this inverse problem, least square. And you can see that the distinct difference between improved resolution. So of course everything comes with a cost. The cost, computational cost of a least square problem is a lot more than just a migration problem. Okay, but young guys should know, you don't worry about cost, computation cost. In another 5 years, the computers are so much faster that you don't have to worry about it, right? Which is true. In the old days, we just, when ERL first formed, we bought a DAC 780, right, Nafi? Yeah. And we had about, I don't think we have 1 gig on that machine. I think we have 500 megabyte, right? Some less than that. Much less than your phone. So this is to show you what RTM can do in an ideal situation. This is the velocity model, and then we smooth it with the velocity. So when we do the imaging, so we can see true reactivity. The RTM, this is least square RTM. One thing you can see, right? We do have tends to have noise around the well on the RTM. Okay, for VSP RTM. So and it does get you a bit better resolution, especially up here when we get a bit more better resolution on the upper surfaces. Okay. So what's extended least squares RTM? In the presence, what we don't have accurate velocity. Conventional least square RTM, you have the forward propagation and the inverse propagators, and you form your inverse problem, right? So when you don't have the accurate velocity, inaccurate velocity, the forward propagation and the inverse propagator doesn't necessarily come in to meet at the imaging point that it should. How do we get a better image? Well, basically, what we do is do a number of iterations or additional calculations with different h's. So moving the improves plus velocity, minus velocity. So, oops. And this is the forward propagator, and this is the reverse propagator. Yeah, basically looking at the position, okay? And this is the extended least square RTM, and the stacked image over half a wavelength of this, over the Fresnel zone, basically. Okay, so hopefully you get a more coherent image, but once again you can see much more additional computation over just a least square RTM.
Does each have a vertical component or just horizontal?
We try both. And right now, the kind of things that we're looking at is the horizontal ones that seems to be more controlling. Okay. At the end of the day, Elita was actually working on this part of it, and she was at here for a little bit. Anyway, what's I going to say? Oh, the paper is coming out with Jizhong Yang as the first author. It should be out in January, geophysics. Yeah.
So the final result, you will sum all of them over the H?
Yeah, someone over H. Over this, yeah, H max of this thing. Yeah. So anybody interested, as I said, the paper is coming out in geophysics this month. So example is the Marmousi model. You get a very smooth input velocity for your RTM, and the least square RTM looks like this when you do the Laplace transform the image, which is the standard way to sharpen the image. You get that over there, and then the extend RTM actually, you can see she sharpens the image a bit more. Okay, now there's a lot. You don't get anything for free. You actually give up certain things, and although the image is sharp, the positions are still not quite correct because you have the wrong velocity. Okay, but the interpreters will like to start interpreting and see what's going on. So, okay. So this is those are synthetic data. What happens in real data? And that was the other thing was pretty much more surface seismic type geometry on the VSP. So we showed you this is a data set from BGP. 2 wells, 3D seismic on there. This is the seismic section. Gives you some idea what's going on. This is what real data looks like. It's not as good as you synthetics. There's quite a bit of noise, some of the amplitude. This is shear offset, the 20 meters. No, this is 20 meters, the 2 wells. Okay. But the reflections you can see very clearly, right? So this one here, this one here. This is farther medium offset. You see, start getting more complex reflections and some of the fading of the arrival in the top layer because it's a medium offset, and start getting the ray path start getting a little bit more horizontal. And this is a far offset. Can you really have trouble trying to really figure out what's going on in terms of what modes, what mode? And that's one of the still challenges going on. So the frequency spectrum are fairly similar. The S603 seems to be a bit more cleaner. S15 is a bit more noisy. So the processing step we're going to go through: setup, amplitude, separation, deconvolution, and separation using ray tracing, PNS wave.
Was the S15 noise, is that an instrumental problem or is it a coupling problem to the well?
I think that's basically a coupling problem to the well. And this is the land data that it tends to be not so, it could be anything. So this is the velocity model we used based on pretty much the seismic velocity, right? Because really you have only control over here and here. This part, the dips and all that has the information has to come from somewhere else. And usually it's the seismic. Yeah. So this is the seismic data overlaying on it, and this is the VSP RTM image overlay on it. So you can see high resolution dip. The problem of the noise around the borehole is there, in this case, the least square RTM cleans up a bit more and gives you the interesting thing, of course, and that's all geometry related. Because of the dip, we are only seeing this part and we're not seeing this, because reflections from here doesn't seem to be going back into the well. So reflection from this dip, this side of the structure, reflects back into the well. And this is extended least square RTM. This one now seems to be able to pick this structure a bit better. And here it's all wrong, actually, it turns out. So each one, has their positive and negatives. But it does, if you expand, so I cut out the triangle to give you some idea what the illumination is, but you actually have more illumination. So if you expand it, you actually do see quite a significant extension on this side, because the geometry allows this to really come back into it. But there's also quite a bit of noise on here. You can do some filtering. You can see these things actually here at the dip. So this is the least squares. And then there's the extended least square. The extended least square doesn't do as well as we like to, because I think the velocity structure is just a bit more complex. So just extending the horizontal doesn't really do it in this case. Okay, so
Clear why the noise near the well seems to be greater on the data set that looked like it was the cleaner data set.
yeah, yeah. So if you just do only up and down separation, RTM and least square RTM image like that, and if you, these two, the extend RTM, it actually extend RTM basically destroy this part of it. So if you do a deconvolution, we're supposed to sharpen the data. You can see this deconvolved data, and this not deconvolved data. You get actually you get more structure, but also more noise on there. Don't know why, because maybe that's not. We should need more sources to get a better image. So this one extended RTM seems to clean up a bit more noise around the borehole. You can see some of the features better. But that's what happens when you actually have real data, okay? And you can run all your simulation with synthetic data, and you won't get this type of answers, because this is real data. The noise in real data usually we can. It's very difficult for us to actually model real data noise and all that. So this is what the VSP can do right now. So what I'm going to talk about is next. Oops, going backwards. Is the source-free converted wave RTM. So we'll go through a little bit of theoretical basis what we're talking about, the source-free converted wave. Numerical example, the simple model and part of the SEAM model, and then conclusions. So seismology 101, or here 521. so mode conversions, right? I mean, all these stuff we've come from MIT a long time ago, right? A lot of for example, the reflection is actually AVO analysis. There's a famous Archie equation on there, right? So using P wave, using S wave, you all know conversion, PP, SV, SV, okay? Are these mode conversion types unconditional? You put it in test 521. This turned out to be not a strict answer. So a new set of equation, clear mode conversion and its conditions. So we actually take the whole equation and expand it with constant density still, but with changing velocity structure. Yelita was working on this. This is Yelita's work, 2018. She was working and continued working in the Hong Kong airport waiting for a plane. And she was sitting on the gate, in the gate, and managed to miss her plane. She was so into doing working on. That's dedication, you know. So this is P-wave propagation, okay? This form the time derivative and the space derivative on the P-wave. This is the source term. This is the P-wave interacting with VP boundary. Okay, this is the VP boundary, delta square alpha, alpha. And P-wave intersects with the VS boundary, right? And this one is S-wave interacting with the VS boundary, okay? So this is the incoming S-wave converted into P-wave on the S-wave boundary. Okay. So this is the S for propagation, S-wave propagation. The source term, source interact with the VS boundary, and P-wave interacts with VS boundary. Okay, so P-wave coming in, VS boundary, you get S-wave propagation, S-wave coming in the delta beta, S. Okay? So insight from the equations. New set equation couples separated P and S propagation in heterogeneous media with constant density. Wave medium interaction can be directly interpreted. Mode conversion only happens as shear wave discontinuities. Okay, that's actually very, very interesting part, okay, going through. So this is P, incoming S, convert P, you have this shear wave incoming P to convert S, also as shear wave boundary. So this is the insight we actually got from it. Okay. So if you don't have a shear wave contrast, only have P wave contrast, which happens in the Earth, depending on what kind of rocks you are, you tend not to get the conversion. Now, most of the time you see both because P and S wave velocity do change, not necessarily together, but they do change, right? The kind of things but there are situations that you don't get a shear wave contrast or very weak shear wave contrast, and you don't get the mode conversions. Discontinuities in VP are transferring to shear waves. Okay, so what is source free now? This is the basics. Source free, the conventional LTM, we take the forward propagated shear wave source and we've back propagated receiver, right? And then you get the PS conversions. Source free imaging condition is actually what we're going to try to do is do this too. Just taking the reverse time from the P and from the S and try to correlate them and see that. Now, the advantage is you are not depending on the source and then source structure. The disadvantage is the angle is very narrow to make it much more difficult in terms of noise. Okay, so this is out in the geophysics this year, this issue too. Paper. Okay. So this is what we're doing. The elastic imaging using acoustic propagator wave equation, fully decoupled PNS wave equation for potential fields. You solve using acoustic propagators. Elastic propagator can generate strong mode conversion when using a rough shear velocity model. Okay, so this is the case. What people doing RTM in particular, of course ray tracing also, there's a lot of influence of the model on the image. So this is the source-free converted wave image using a fully elastic propagator and using two acoustic propagators for P and S. So you can see elastic propagator really seems to do a lot better. So why are we even care about acoustic propagator? We pay a bit more, but you get a better answer. Well, it turns out, is this correct? How much of the inference is the imprint you have velocity on this? Well, we'll take the simulation results, okay, from this model, from the PNS wave data, and then we do source-free converted wave imaging RTM using a wrong velocity model. In this particular case, we flip the velocity model 180 degrees. What you see then, all of a sudden, your source-free image basically mimics your velocity model you use. Whereas the acoustic propagator basically said, no, this is completely wrong model. Okay, so one of the things that we always have to be worried about is the model imprint on it. You're using an elastic propagator. Basically, if you know the answer, you get good answer. If you don't know the answer, you don't even know whether you have a wrong image. Okay, so the SFCW image is a second order approximation of velocity perturbation. So that's actually weak. The degraded resolution because of a narrow angle range between PP and PS, and strong artifact across top of PP and S from the different reflectors. So this is good idea, but it's not necessarily the best thing that you want to do. Now, what is good about SFCW? Why are we even looking at it? Well, we're doing some numerical example to demonstrate what's going on. So this is a simple example. You do a PP. These are the simple structures, PP, PS image, and source-free image. You can see that these are better images. And this one has it's synthetic data, be okay. Not a bit more noise. Okay, watch the red line, which is where the structure boundaries are over the image. If I use the SFCW, avoid, because you're using just these two, you're not using the forward source propagation term. You avoid an uncertain overburden structure. Okay. So if I use a wrong or slower velocity in this structure to image that, you can see that the P and the shear image actually got pulled up. Okay, they're not in the right position. However, the source-free converted wave, because it doesn't depend on this layer, still remains at the same place. Okay, so that's why source-free still has quite a bit of use in a VSP type situation like this. So, and this is the CM2D model. We want to cut it out, and looking at this, and you can see the model is fairly complex on the P and the horizontal. This is the vertical, this is the horizontal, PP and PS. you can see the reflection coming back further in time. And this is P coming in, PS and PP. And these are where the reflections are coming through. Things that coming off the salt flakes are things down there. Okay, so the PP image looks pretty good. We actually can see parts of the side of the salt, not completely. We can see this lower part of the salt, and we can see a lot of these sediment layers coming through. Okay. The VS image sees different things. You see a bit more conversions on the shear, and you get a higher resolution because of the slower velocity and the smaller wavelengths, and the less defined salt image. Okay, and the source free basically cannot see the salt. You can only and can actually not see that much. You only see very nicely the near borehole conversions. Okay. So, however, if we cut out this part and focus on this, and the PP image, PS image, source free image, you're looking at the red arrows, looking at the reflectors. Okay. Each one gives you different information, and if I use a faster overburden velocity, you see PP got moved, PS got moved, but the source free remain the same. So the PP and PS, because you have the source propagation term, it ends up the image location is being influenced by the velocity more. The source-free converted wave, because it doesn't need the source term coming back, just looking at the two reflection term, both from the borehole, it end up giving you a very stable near borehole image. Okay, so the events in PP and PS are pushed down by faster migration velocities. The overburden velocity error has stronger impact on the shallower layers. Okay, so this work utilized elastic imaging condition with acoustic propagators, equations for VSP LTM to image complex structures. The advantages of using the acoustic propagator for elastic imaging: the lower memory computational cost, free of artifacts caused by unphysical mode conversions, imprint of shear wave velocity model, in situ mode conversions, etc. There's a lot of imprint like this. But the thing is, you need a clear PNS data separation in recorded data. Okay. The near borehole, if you don't have a large offset, the separation of PNS wave in VSP is fairly standard. Some are better than others, but it's a very standard thing. But you have far away, then that's a challenge. Okay. Model building, we still rely on seismic, surface seismic data to build the model, because we have limited aperture and coverage. How do you extend from the well measured velocity to 3D? You really cannot do it that well. Using VSP tomography is very, very poorly constrained problem. You can do seismic migration velocity. So we need to define the structure. Wave view separation, how can you separate PNS wave? You clean it in complex environments. That's a challenge. Large offsets is a challenge. Is this up and down enough? In some cases it is. Challenges still imaging. Under what conditions are each method adequate? CDV, Armstrong, Kirchhoff, and RTM. What kind of wavefield separation needed? Shall we use elastic RTM? You know, actually, people have used elastic RTM before, and they have run into problems. That's why they actually end up giving up doing elastic RTM on the 3D VSP issue. Least square RTM, do we really need it? I think one of the things is the cost. Right? I mean, maybe in 5 years that you need to revisit that. Well, other methods. Well, that's a. So finally, before I wrap up, Doug is there. He might not agree with what I say. So, yes. So the amount of data and ability to collect over the entire world is very attractive. I mean, this is what was driving it, right?
What's your first slide was DAS, wasn't it?
Huh?
Your first slide where you explained VSP was a DAS. VSP.
No, that's not DAS. That's a really close. Maybe there was a DAS. I pull a VSP somewhere, right? It could have been a DAS.
If there's 2 meters per channel, it's DAS.
Yeah. Single component, which part of particle motion is senses changes with incident angle and well depth, really. I mean, that. So, amplitude variation is a big issue. So right now it's suitable for kinematic space applications, not for amplitude blades, okay? Specialized fiber might be needed to fully realize the potential of DAS. Go back one. So let me just amplify this a little bit more. So last year at SUG, there are a number of papers talking about basically taking the fiber and putting in periodic levels, little cuts or whatnot, notches to increase the effectivity. So there are people looking into that, doing that. So Yelita has been working on this using from the optics side. Which turns out that she has submitted abstract to EAGE. So turns out that part of the problem, what you see in the amplitude variation, is due to the randomness in the fiber and the incident angle. And unlike geophones, which basically are point measurements, when the wave field you measure a point, fiber, the way DAS works is you actually have to average it over a certain distance in the fiber, and depending on the property of the fiber and the randomness of it, it does give you variations, and also, so that is frequency dependence, because how much the wave field the fiber sees. Now, if you say, okay, I am 50 meter wavelengths and I'm only sampling over 1 meter, maybe that's not an issue. But other cases that could be an issue. So these are things that we need to think about. As geophysicists, we tend not to think about some of these things, but as engineers, we do, when we build equipment and actually give you the data, we do think about these kind of things. So there's something that at least that's my opinion of what's going on at the moment. So, okay. Thank you. Not too bad, it's only 5 minutes over.
Well, I will thank you very much for an excellent I don't know, tour de force or something like that here. And I could see that the students and the postdocs and so were very quiet,
Yeah.
very involved in listening. And I think what you gave them here today is really something very special. I hope they think about it as a kind of a quality control. This is the kind of stuff we want to see. And I really appreciate it. So let's entertain a few questions if you have for Professor Arthur Cheng.
Yeah, stuck.
Just a comment that might be of interest to the group in this room. On the subject of DAS, about 3 or 4 years ago, I published a number of papers, but I published one in particular with Tom Daly of Lawrence Livermore Lab. It's published in Physical Prospecting. The paper is available on my MIT page. The data from that paper has just been uploaded to a public archive. It's a complete VSP done both with geophones and with DAS. And so anyone who would like to revisit some of that work and use it to educate
great.
themselves, that
Yeah.
data is now available in the public archive. See me if you want more details. We just got it up in the last few weeks, but it's there.